Now let us consider the following functions and describe the behavior of the function at each zero in the denominator using negative or positive infinity when appropriate. So let's consider the second example here, the function f of x equal to x minus 3 divided by x squared minus 4x plus 3. So we begin by computing the zeros in the denominator. So we do that by factoring. So the 0 x squared minus 4x plus 3, the 0 of this can be computed by factoring, or you could also use the quadratic formula if you can't factor it. So you have x minus 3 times x minus 1. Equate this to 0. Now, you equate each factor to 0 because the product is 0. That means that each factor here might be 0. So x minus 3 might be 0, or x minus 1 is equal to 0. After that, you compute for the x here, or the zeros for each of this equation here. So if x minus 3 is 0, that implies x is equal to 3. And if x minus 1 is 0, that implies x is equal to 1. When analyzing the zeros in the denominator, bear in mind that there are two possibilities. Either one of these is a whole, or one could also be a vertical asymptote. To find out, let us plug in these values of x to the given function. So let's take, for instance, let us consider plugging this in to the function x minus 3 to the function. Now, if x is equal to 3, our function will become 0 over 0. Because x minus 3 is a 0 in the denominator. So if I plug this into the denominator is 0. So we have 0 in the denominator, and it would also make your numerator equal to 0. If you have a 0 over a 0, that means that at x equals 3, we have a hole on our graph and not a vertical asymptote. Now, let's consider the other value of x at x equals to 1. And then let's plug that into the function. So let's evaluate the function at x equals 1. At x equals 1, the numerator here, if you plug in the value of x here, 1 minus 3 is equal to negative 2. And then the denominator is also 0. Now, if we have such a case, we then say that x equals 1 is a vertical asymptote. Now, we know that if a function is approaching to a vertical asymptote, the function will either increase without bound or decrease without bound. That means that the limit of the function as it approaches this value of x here, or the vertical asymptote here, is either positive or negative infinity. Now, to determine whether the limit is approaching to positive or negative infinity, we look at the limit at the right side of 1 and at the left side of negative 1. That means we will compute for the left-hand limit and the right-hand limit at x equals 1. And to do that, we will first simplify the function here. We will write the function in its factored form. So the numerator is x minus 3. The denominator in factored form is given by this one. So we have x minus 3 times x minus 1. And then you cancel the common factor. Note that in this common factor at x equals 3, so at the 0 of that common factor, the graph has a hole. Then we're able to now get an equivalent expression for the function. This is x1 over x minus 1. Now this new function here is or has the same graph as this function, except that it has this function here has a hole at x equals 3. Then let's now take the limit of the reduced expression, this expression, equivalent expression, as x approaches 1 from the right, and the limit of that same expression as x approaches 1 from the left. And so to evaluate this, you just have to plug in 1 to the expression. You have 1 over 0. So you say this x minus 1 here will approach to 0 as x approaches to 1 from the right. Now we wanted to know which side of 0 are the values coming from as this expression here approaches to 0. Now to do that, you get a representative point from the interval here. So if x is approaching 1 from the right, it is coming from the right side of 1. So a representative point there could be 1.1. So now if you subtract 1.1 and 1, that is a positive value. So 1.1 minus 1 is greater than 0. So that would imply that the values are coming from the right side of 0. So this becomes 0 positive. So 1 over 0 positive is equal to positive infinity. Similarly, when we evaluate the limit for the expression here as x approaches 1 from the left, we do the same thing. We plug in 1 to the denominator and we get a 0. And then we determine where the values are coming from as this expression here approaches to 0. Now to determine, we are going to get a representative point from the interval here. So the x's are coming from the left side of 1. At the left side of 1, those are the values less than 1. So we could use 0.99 in this case, 0.99 minus 1, and then just determine the sign. That gives you a negative value. Therefore this implies that the expression approaches to 0 from the left side of 0 or from the negative values. So therefore you have 1 over 0 minus. So therefore this is equal to negative infinity. Now let us consider the third function, f of x equal to x minus 1 divided by x plus 3 squared. Describe the behavior at the 0 of the denominator. Now the 0 of the denominator here is taken from x plus 3 equal to 0, because the denominator will only be 0 if the base here, which is x plus 3, is equal to 0. So if x plus 3 is 0, that implies that x equals negative 3 is a 0. Then you check whether at this value of x you have a hole on your graph or you have a vertical asymptote. To do that, you just have to plug in that value to the function and evaluate the function. Now, if x is equal to negative 3, you have negative 3 minus 1 divided by 0 squared. And simplifying this, you get negative 4 over 0. So we got something of the form constant over 0. So if you have constant over 0, that means this one is just either a plus or a minus infinity. So this means that at x equals -3, we have a vertical asymptote. Now, to describe the behavior of the function at x equals -3, we will proceed to find the limit of the function at the right side and left side of -3. Now let's go ahead and evaluate the limit of the function as x approaches -3 from the right. So we do that by plugging in -3 to the expression here. We have the same value, -4 over 0. The next is we determine the sign of 0. Now notice that this expression here is raised to 2. So that means that no matter what you input to the value of x here, the expression here will always be positive or equal to 0. So this means that the 0 here will have a plus no matter what the value of x is. So similarly, if you also get the limit of the same expression as x approaches -3 from the left, this would still result to -4 over 0 plus, because again, this expression here is raised to 2. So if you have -4 over 0 plus, that gives you -infinity. That means you have -infinity for both limits. So that means the left-hand limit and the right-hand limit as x approaches -3 are both equal to -infinity. From here, we could also say that the limit of our function f of x as x approaches -3, so if you remove the sign, you can then say that this is equal to -infinity.